Well, welcome back to 267. I'm going to talk today about yet another type of parallel hardware, which is graphics processing units, or GPUs, and try to give you an idea of both a little bit behind the architectural trends that have led to the popularity of GPUs, especially for things like machine learning, but also then how to go about programming them. So I've taken lots of slides from lots of other people. I haven't put each of the acknowledgements on every individual slide, so I'm just acknowledging them all here. So especially in high performance computing, although this comes up actually at every scale of computing, the question of the energy use of the supercomputers is a big driver. It is a substantial part of the cost of ownership of one of these large scale computers, whether it's in a cloud or in a scientific computing facility such as NERSC. Just to give you a rough order of magnitude, and I know this from having been the NERSC director, the cost of a megawatt, if you're running a system that is a megawatt, that costs you about $1 million a year in order to power that system. And these top systems, if you look at something like the Summit system, that has about a $10 million power bill, electric bill every year. Now, we get somewhat better pricing on this at the labs, but nevertheless, that gives you some sense of how expensive this is to run. And back in 2018, when we first started thinking about trying to build an exascale machine, we were looking at, if we just sort of projected out with some assumptions about scaling, and there was a study done by DARPA about this, there was a projection that it would be 200 megawatts. So now you've got an annual budget at NERSC of around $100 million. You need twice that just to pay the electric bill. It doesn't leave you much to, doesn't leave you any money to buy any hardware or anything like that. So what has happened since then is we've seen some of these other machines that are at the very top of the list. So the largest machines in things like the Tahane 2 and the Taihu Lite machines at 18 and 15, whoops, I think I have those reversed, megawatts, and then Fugaku at 28 megawatts. So these are obviously the power requirements or energy requirements for these machines have indeed been going up over the last few years. And as we're looking ahead to exascale in the next year or so, I would guess that those machines will come in at somewhere between 40 and 50 megawatts. So not what our goal was to try to get it down to 20 megawatts. So back factor of 10 from the sort of normal scaling. Probably won't get quite there, but certainly better than the original estimate of 200 megawatts. So if you're all about energy use and how are you going to design this hardware, and by the way, this is really true whether you're talking about building a cloud center or you're talking about building a supercomputer, the power is mostly in the processors, the memory system. There's certainly some in the interconnect. I mean, it's certainly a lot of it is about moving data around, but it's not really about something that makes an HPC system unique. So these are the same kinds of power estimates. And if you look at how much power is in some of the big cloud centers, it also would be tends to even 100 megawatts or so for those types of large scale facilities. So this is a big concern. So where did GPUs come from? Well, GPUs originally came from graphics applications, of course, as the name suggests. And graphics applications included things like games, which Jim talked about last week in his Sources of Parallelism lecture. This is an image from the Martian movie. And this is really about the fact that now graphics processing units are also used a lot in making films. So there's a lot of specialized computation that comes up in some of these media sorts of applications and graphics applications. You're running over the pixels on a screen. Those pixels can be stored with fairly narrow data types, but there's also physics that comes up in both the game scenario and also in making realistic movies. Even in something like Finding Nemo, they did a full fluid dynamics simulation for the ocean. Interesting, aside from a friend of ours that was working on that movie as the person in between the mathematicians, the computational scientists doing the fluid dynamics, and the director was that little particles would float in front of Nemo's face, and they would, and the director didn't like it from an artistic standpoint. So by the time the movie was actually completed, there was somebody whose full-time job for that a number of months was just to zap the particles that didn't fit with the artistic nature, but were in the fluid dynamics simulation. So what's inside of a GPU? We're not going to look at this in a lot of detail, but there are these different kinds of cores. There's some very specific things for texture mapping. It is basically a heterogeneous specialized processor that has these different kinds of building blocks in it. Also has something called a work distributor that sends computations to these different parts of the chip, and that can use a combination of hardware and software. So it's a heterogeneous chip multiprocessor with, the heterogeneity means there's different kinds of cores on it that are somewhat specialized to the computation. Now, over the last decade or so, the GPUs have become more general purpose. And so, in fact, sometimes you'll hear the word GPU, which stands for a general purpose GPU, which is a sort of seems like a contradiction because it's supposed to be specialized for graphics, but it actually has become used for a broader set of applications, including both simulations and machine learning. So what's inside of a CPU? Let's look at that by comparison and see how the GPUs get designed then to be much more energy efficient, going back to my original point. So we're going to try to figure out how to get high performance in a more energy efficient way than we get in a CPU. So just with our little cartoon here of a CPU, we have what the fetch and decode unit, which is going out and taking each instruction in the instruction machine and in this instruction stream and figuring out what it is. Then it uses that to issue things that are going to be operating on the arithmetic units, the ALUs. So it's executing things. And there's some context down here, which would include things like registers and perhaps and other things. But what the other things that CPUs have are out of order control logic. So you saw this as you are optimizing the matrix multiply code. You're trying to coax the hardware into generating the right sequence of instructions in order to maximally use the pipelines that are in the hardware, but also to issue things out of order if they can be done out of order to give you a better instruction mix, which will give you a better efficiency on the hardware. Fancy branch predictors, because something that's very expensive is if you aren't going down a predictable branch, then you can't prefetch and things like that. So you're trying to predict which direction the branches are going, and the memory prefetcher, which is loading those values into, say, a level 1 cache, so they're ready when that iteration of the loop comes around. And a big, huge cache. In fact, probably multiple levels of cache, but even on the chip, at least there's going to be some level of cache, and that will take up a substantial amount of the real estate on a CPU. So the first idea in GPUs is to really get rid of a lot of this complexity and the extra stuff here that was specifically designed to make serial code run fast. So things that were trying to automatically discover parallelism, which was whether it was parallelism between the arithmetic operations so that you could schedule them in a different order and get the right instruction mix, parallelism between the memory operations and the computation so that you could prefetch or delay the writes or things like that, and then the caches, which are there to try to optimize for serial performance as well. So getting rid of some of this real estate and simplifying substantially the processor is one of the first things that we do, that a GPU does. So now the next thing we can do, of course, is now we've got more real estate on the chip. We can make multiple copies of this. We do this even in a multi-core setting where we have these very sophisticated processor cores. But in this case, we're in a GPU, we're going to put, because we've simplified the cores substantially, they're much smaller, they take up less area. So we'll put a very large number of these cores on the chip. So hardware idea number 2 is put a larger number of smaller, simpler cores onto the chip rather than a more modest number. So this has got a picture with, say, 64 cores. That might be a typical number that's in one of these kinds of, even today it might be in a multi-core chip, but originally this was in the, and we'll see a much larger number than even going on to a GPU. But we have to make one more change next. There's all this parallelism now that you have to exploit. And what this is doing is taking all of that work that the hardware was trying to do automatically and turn your serial instruction stream into a parallel code and turning it in, and instead saying the programmer has to write parallel code. And it's one thing if you've got, say, 2 or 4 cores, you may find a couple of different tasks. If you're running even on your laptop or your cell phone, you have something that's updating the screen, you have something that's updating your email, you have a few different processes that are running. But for this scale of parallelism, when you get up to tens or even hundreds or even thousand-way parallelism, it's very unlikely that you're going to find 1,000 different things to do in parallel. So that will force us into really looking at data parallelism. So in data parallelism, we're going to do the same thing on different data items, such as computing over an array. And you saw this already if you've started looking at your OpenMP work, where you're looking at a loop and you're parallelizing that loop. That is typically going to be data parallelism, because every iteration of the loop is doing roughly the same thing, especially if you don't have branches in it, then it is. So the third idea is to say, well, if what we're really going to exploit is data parallelism, then we don't need to fetch and decode all these separate instructions, because all of these different processors are actually running the same instruction. And it may not be obvious, but there's actually a fair amount of work that is required to go and decode those instructions, to get something out of the instruction stream and decode it. And so big idea number 3 is to share the instruction stream. So we'll build we'll take all of our ALUs. Here we've got 8 of them on the chip, and we've got just a single fetch and decode engine. So this is going to look a lot like SIMD, right? In fact, this is really what a SIMD instruction is doing, which you saw in homework 1. So we've got these different arithmetic units that are operating on, say, different elements of an array. In a SIMD, pure SIMD hardware, those are typically things that are contiguous in memory, maybe cache aligned, but there's some special rules on it. The GPUs are going to try to generalize those a bit more and try to generalize this idea, and also make the SIMD units much wider. But the basic idea is the same, which is that you can amortize the cost of some of that instruction stream analysis, the fetch and decode, by having just a single fetch and decode engine, and then a whole bunch of arithmetic units that go with it. Now, I tend to like to think about this as SIMD because it's something familiar from the CPU arena. NVIDIA will tend to call it SIMT, so single instruction, multiple threads. And that has to do partly with the way we're going to program this. We're really going to program that in a way that's fairly different than in the SIMD CPU model, where every once in a while you've got a bit of code and you'll stick in a SIMD instruction, or hopefully the compiler will generate it for you. And you've got sort of serial code that's serial by default, and then kind of widens out into one of these SIMD operations. Whereas in the GPU, we're going to try to sort of make everything parallel by default. And so we're going to have all these threads that are running in parallel, but some of them are going to be doing the same thing. And so they can take advantage of this similar kind of hardware. The stuff on the bottom, by the way, is what I've shown here as context. It's got some thread-specific context as well as some shared context. And that'll come up again. Those will be things like registers or memory, where we can store the information that we're computing on, the data we're computing on.
Would the assembly code look like say for add, where you have in RISC, like destination and then the 2 registers to add? Like, so here, would there be like 24 of those? Like 8 destination and then 16 registers to
Right.
add?
In an 8-wide SIMD, well, so typically what you would do in an actual SIMD instruction, and exactly in the GPU hardware, it's going to look a little different because we're going to have something called a warp. But in this sort of SIMD instruction, what we will typically have is a single address, and then just say take the 8 values, to the right of that for both the let's say you're doing a vector add. You've got 2 addresses you're looking at, or you've loaded them into register already and you're pointing at these registers, but the registers are actually 8 values wide, so they're wider values. So the instructions are referring to all 8 of those values at once, not referring to, you don't have a separate address for each one of them. Does that answer the question?
Yep.
Great. Okay, so fine. We've got the SIMD type of execution model where everybody's running the same instructions. We only have to decode one of them. We've got a whole bunch of ALUs, at least 8 of them here in this little cartoon. But what about branches? Well, if we're kind of computing along in time here, and we've got some code that doesn't have any conditionals in it, it makes the SIMD unit, the SIMD execution style, very happy. Everything is executing in parallel. But now we get into a branch. And so we've got a branch that has a different value on the different threads. Then what happens in this data parallel sort of SIMD execution style is you have to turn some of them off. And so this is going to end up, we first execute the if branch, for example, that has a few instructions that are being executed with these 3 threads still active. And then we'll execute after that the else branch, with the other threads, the other 5 threads that are active at that point. And so obviously this is not a very efficient way to use the hardware. One of the things that's down in the details of the microarchitecture and some of the latest GPUs is something to try to make this more efficient, but it's still a good model to think about in your mind in terms of what's happening in that GPU is you're going to have this chunk of this instruction that, or this operation that's very wide, and it's going to be even wider than 8 arithmetic units, and that roughly speaking, you want them all to be doing the same thing as much as possible, or you're going to lose efficiency. And note that it can be worse than just 50% loss of efficiency. If you have nested conditionals inside of here, at some point you may be running on a very small fraction of the processors or of the ALUs. And now the hardware handles these details of the masking inside of the GPUs, but if you've written this kind of code that has these conditionals in it that the compiler and the hardware can then analyze. But nevertheless, from an algorithmic standpoint, and that's why on Thursday, I'm going to talk a lot about data parallel algorithms and what is sort of an abstract way of thinking about these algorithms that will end up generating lots of things happening in parallel and try to avoid these kinds of branches. And we'll also be more explicit about thinking about the fact that we're masking things in these data parallel algorithms. So the next problem to think about is, remember, one of the things we threw out of our CPU when we tried to make it more energy efficient to make it a GPU was, well, a couple things we threw out. We threw out a big, huge cache, and we threw out the prefetch engine. And so that means that a core, one of these little ALUs that's executing along, they're all running the same instructions. If the next instruction depends on a value coming out of memory, for example, it may have to stall while that value gets loaded into a register. And that will be very inefficient. You've taken your huge arithmetic engine that's got 8 or 64 or whatever wide parallelism in it and stalled it because one of them is waiting now on a dependent value. And so, and these memory operations, as we know, are the most expensive thing you do on one of these processors, hundreds or thousands of cycles. And as I said before, we took off some of the hardware that we needed to make that stuff go fast. So in order to optimize for throughput, what we're going to do in a GPU is just use more threads. So rather than just having 8 threads, we'll have, say, 32 threads in this little cartoon here. And so if one of the groups of threads is executing on our 8 arithmetic units and it's running along and it hits a stall because it's, say, waiting for a memory operation, then you'll just switch to the next group of threads and run that. And this happens much more efficiently on a GPU than it does in something like an OpenMP loop that's running on a parallel, on a multi-core system, because it's being done in hardware. So the hardware is actually context switching between these different groups of threads. And so that will, and the purpose of this is to hide the latency. So one of them stalls, it runs something else. By the time it loops back around and the first group of threads is ready, it is running again. Hopefully that value will be, the value will be in memory. Obviously, we probably need more than 8 groups of threads if we're going to have to wait for 100 cycles. So what we're going to end up with then on this, on these GPUs is these, what are going to be called streaming multiprocessors, these that have these single fetch and decode engines, a bunch of arithmetic units in control, states, the registers, and some local memory. But then we're also going to put a whole bunch of them together on a chip. And so this abstract chip has 16 of these GPU style cores. And let's say that it can do 8. It's got these 8 arithmetic units, each of which can do a multiply add, a fused multiply add instruction per cycle. Let's say that they're running at 1 gigahertz, and we've got this chip is going to be a 256 gigahertz flop chip. Okay, so that's sort of a cartoon and the motivation of why GPUs look the way they do. They're going to use a lot of data parallelism. They're going to have fairly lightweight cores. It's going to require the software do a lot more work to discover the parallelism, but now we'll get a little bit more concrete in terms of what they look like. But I want to check and see if there are any questions first. Okay, so let's go on. This is the sort of GPU hype, which is a slide from NVIDIA that shows single thread performance going up over from 1980 up to not the mid, I guess, teens, 2016, 2017, something like that. And you can see the performance shrinking to about 1.1x per year, whereas the GPU performance was going up still by 1.5x per year. And they projected out a factor of 1,000 by 2025. Okay, so you'll hear these kinds of numbers around GPUs that it might be a factor of 100 or even 1,000 faster. But I went and looked at a paper that's done a recent benchmarking analysis of it. And there is a substantial difference between the CPUs and GPUs, but maybe not quite what we were seeing. And sometimes, in some cases, the CPUs are getting closer. So I wanted to, even though this lecture is about GPUs and there is a tremendous efficiency advantage and a level of parallelism that comes from the GPUs, we should be a little bit more careful about what you're actually getting from the CPUs versus the GPUs. So this is a paper, and I will add the citation to it, but it was looking at these CPUs are all of the round circles down at the bottom, the lines are the round dots, and the GPUs have all the crosses. So you can see that over time, there has been a substantial difference. This is though a linear scale between them, and this is in teraflops. So you can see that there are some cases where the CPUs may have caught up. I think that one is actually the AMD EPYC CPU. Is that right? No, it must be, that's the Intel Xeon, and that may be the Knights landing processor that had much wider, they're adding both wider SIMD units and more cores, whereas something like the Cori KNL system, of course, has 68 cores per chip. So that's when you start to see that gap closing a bit. That was single precision floating point performance. This is double precision. Historically, the GPUs haven't always had double precision floating point, so sometimes it was very slow. But in recent years, because it is used for a number of different applications, they're putting these in large-scale HPC systems that run the 64-bit arithmetic a lot, and it's used in some parts of machine learning algorithms as well. That you've seen this boost in the 64-bit arithmetic. So this is what the overall picture looks like for a GPU node on Cori. We call it a GPU node. It's really a heterogeneous node. It has CPUs, so 2 Intel Xeon processors and 8 GPUs on it. So and they're connected together by a PCIe switch, or a PCI Express switch, and they also the Xeons themselves can talk through a different interface called a QPI network. But this is kind of what the picture looks like. Oh, another important thing on here, the little pink rectangles are the high bandwidth memory. So this is HBM2. One of the things that makes GPUs fast is not just the amount of parallelism on the chip, but the fact that it is putting a certain amount of very expensive, very high bandwidth memory next to the GPU in order to keep that GPU fed with data. And you might ask, well, why not do that with a CPU? And people do look at and do put these high bandwidth memory systems on CPUs as well. But GPUs have the ability to then kind of issue lots of bandwidth requests because of all of their massive parallelism. And this is specifically the GPU that's inside the Cori nodes is called the GV100, or the Volta or V100 processor. And so it's usually called the V100. And inside of here are these 4 SMs, and inside the SMs are, well, this is one of the blocks actually within the V100. And so it has even more of these associated with it. But inside of one of these blocks is one of these things that looks then a little bit more like our cartoon did before, what a GPU looks like. It's got a dispatch unit. So that's looking at is keeping track of the instructions. And there's some registers here. There's floating point units for both 64-bit and 32-bit floating point, twice as many of them for 32-bit than for 64, and also integer units at the same number. The 32-bit integer units at the same count as the floating point, the 32-bit floating point. There's also some special processors for tensor cores. These are going to be doing things like 16-bit arithmetic and are really specialized to the kinds of computations that come up in deep learning algorithms. And over on the right, you see some of the total sizes of these things for an SM. So an SM is their name for this kind of this processor unit, this streaming multiprocessor inside of a Volta. So let's see, I think this says, I just sort of wrote down in a little bit more detail for your reference what's inside of these, but I won't read through this slide. So these are Skylake Xeon processors, 2 of them, and in the that are at 2.4 gigahertz, and then the 8 Voltas. And here's a roofline model that somebody at NERSC did, which is looking at a synthetic benchmark here. So this NW is really just measuring the amount of computational intensity. So it's a synthetic benchmark that just has a loop and is doing more and more computation in that loop, depending on what this NW number is. And so you can see, we can use this roofline model here. We've got the HBM memory bandwidth over here in the diagonal line, and we've got the two roof lines for the fused multiply add and no fused multiply add, and then the computation being laid out on that as well. Okay, any questions about that? Let's see, there's one in chat. So the question is, why can we fit more cores into this space, but we can't fit a bigger single threaded processor into the same space? We can fit a bigger single threaded processor into the same space, but with the benefit that you're getting from making that the single threaded processor, or that single kind of core, even if it's got some level of multi-core parallelism in it, all of that real estate that you're using to try to make single thread performance better, such as the prefetchers and the out of order execution engines and the caches and things like that, they're not very efficient because they often fail to find enough parallelism. And you've also then taken up real estate for those rather than just putting more parallelism on the chip. And so that's one of the reasons that the GPU says, let me push all of those problems basically up to the software level. Well, use multi-threading also to mask latency rather than prefetching, and so we can cram a lot more of these simpler cores into the same area than we could the more complex cores. So there's a question about the tensor operations, and we may talk more about this when we talk about machine learning later in the semesters, but one of the differences is those tensor operations are not doing 32 or 64-bit arithmetic, they're doing 16-bit arithmetic, or at least part of the arithmetic they're doing is in 16-bit. And so that is something that you may be able to do at about twice the speed of 32-bit or 4 times the speed of 64-bit in terms of the amount of parallelism. So not because the clock rate is faster, but because the amount of, because you need half as much hardware for a 16-bit operation as a 32-bit operation. And so that's one of the main differences that you'll see inside of the tensor operations. They're also somewhat specialized to the particular pattern of data movement that comes up in tensor computations, which we'll talk more about them. But if you think about these sort of matrix operations, dense matrix operations, that will give you an idea of what those computations look like. Okay, so we're in this class, when you're doing your homework assignments on the Cori nodes, you're actually going to be using just one of the 8 GPUs, not all 8 of the GPUs. There is a way of programming the 8 GPUs together to sort of communicate with each other directly rather than going back and forth to the CPU. But we'll be using one of the GPUs at a time right now. And that's often the way the system is used anyway, because people will use a different kind of parallelism, message passing parallelism, MPI parallelism for each of the GPUs, which you'll be learning about next week when Aiden is talking about MPI and message passing. But let's just think about a couple of the components on the Cori node, which is one of the CPUs, the Skylake processor, which has 40 cores, they're each 20 cores in each of the 2 chips, and a GPU, one of the V100s, which has 80 of these SMs. The V100s have up to 84 of these SMs. I think what they're doing here, one of the other reasons that people put these lightweight cores onto the chips that I may have mentioned before is for yield reasons. So some part of the chip is often bad, and if you've got 84 of these processors on it, you can turn off a few of them if they're bad, and the rest of the chip will still work. So I think the ones that are inside Cori seem to have 80 of these SMs in them. So what is it like to write a program where you've got a CPU and a GPU, and you're trying to sort of manage both of them together? Well, what happens is the CPU is kind of where your program runs by default. And so this is where the operating system runs. This is where a lot of the communication between the nodes will be done. A lot of those kinds of things will happen. Complicated code that doesn't map very well onto GPU parallelism or doesn't even fit within the programming model of the GPU is going to be running on the CPU. And an application, the way you can adapt an application fairly easily is you start with the application and you incrementally add bits of GPU code to some of the loops. for example, where you think there's a lot of computation. This may not be the best way to get really great performance. You may want to rethink the entire application, but nevertheless, this is what your application will do in the end, is probably run some amount of CPU code with some amount of GPU code mixed in. And so you'll start out, say, running the main function, and you'll be in the CPU, and then it will spawn a kernel, and that will run in the GPU, and then it'll come back to the CPU. And by the way, these things can also be overlapped, but for right now, we'll just worry about the fact that we're going back and forth between CPU and GPU code. So here's a simple example. This is vector addition, and I'm just going to show it to you so that we can just sort of familiarize everybody with the variables and everything in here for just a traditional CPU application. So we've got our main function. It's building, it's saying we're going to do a vector add on 1,000,000 elements. It's a very contrived example. We're not taking any input values. We're going to just declare 2 floating point arrays, both of size n. And at the end, we will delete those 2 arrays, x and y, and just do a return from this. So what's the main computational piece of this is we're going to initialize x and y on the CPU. So we just run through this loop and filling in some sort of dummy values, a 1.0 into x and a 2.0 into y, into each one of the elements. So as I said, not a very interesting example. And then we run some function, which is really the main thing that we're interested in here, which is the add function. And we run that on the CPU. And that takes in the 2 vectors, x and y, as well as the length of those vectors, n. And here's the function add over here. And it is serial code. So it's just running through each one of the elements on this. One of the CPUs, one of the cores on the CPU is running this code, and it's active, and it's just going to run through this element, this array of n elements, and add up x and y and put the result in y. Okay, so as I said, just to sort of get everybody normalized, this is what the code looks like. So how does this change if we want to run just that add function on a GPU instead of a CPU? Well, what are the steps that we have to do is we have to, first of all, allocate some memory on the GPU. We have to copy the data, the input data from the CPU into the GPU, execute the GPU program, wait for that GPU program to complete, and then copy the results back to the CPU. And so those are all of the steps that are the main steps that are involved in doing this. And this, by the way, this communication, just to remind you, is happening over the PCI or PCI Express bus in between the CPU and the GPU. So this is not just memory that you can all, share easily. One of the things that Volta has done, and the V100 has made this a little bit easier, but I'm going to look at the more traditional way of explicitly copying back and forth. So here's the GPU version. Now this is a very dumb GPU version. In fact, this will run much more slowly than the CPU version because it's going to run one of these little wimpy cores, one of these little SMs using one of the ALUs on one of these GPUs, and so on the GPU. So it's really going to be a very inefficient GPU code, but we'll just start with that so that we can see what it's like just to go back and forth, but just to call a GPU kernel. And so we had the same initialization code. This all looked the same, and we got the allocation, the free, that was all happening on the CPU, and that part of it hasn't changed. So I'm just deleting removing the initialization code from the screen so we can see everything else, but you can see the variables here, x and y, that get that are still allocated. These are allocated, as you can see, these yellow bands over here on the CPU are the arrays x and y. And we presumably filled them in, but we're not showing that. Then we go into, we need to allocate some memory on the GPU. So we're making up 2 other variables. So these are also declared in the same way. They're a pointer to a chunk of floating point values. And so dx and dy. And so these are the device copies of x and y. And that's sort of a common convention in GPU code, is to name the device copies of something that's on the CPU with the same name, but with the D underscore in front of it to say that it's going to be sitting on the device rather than sitting on in the CPU memory. And so how do we allocate something in the GPU memory? We do it with a special kind of malloc, which is the CUDA malloc. And so CUDA malloc is, you can see the syntax here, a bit ugly, but anyway, and we're getting back a pointer then to a chunk of data that's been allocated, these yellow stripes over here in the GPU memory. So dx and dy are pointers to those 2 arrays. And at the end, by the way, we should also free them, at least good programming style. And so the CUDA free operation is used to do that for memory that's been allocated on the GPUs. Now we have to copy the input values. Remember, we filled in X and Y with some floating point values. We need to copy those into DX and DY. And that's done with a CUDA mem copy. And both on the way in, so copying X into DX and Y into DY. And you can see there's something that says I'm copying the host to the device. And then in the result, when it comes back, I'm copying the device to the host and copying DY into Y. And so that's getting the result of the vector add out. And I'm going to have to then actually call we still have to call the code. So we've done the copy to the GPU in both directions here. So what does the actual function call look like on the GPU? Well, it has this funny triple angle bracket or triple chevron syntax. So it's calling the add function, which is a special add function that's been defined for GPUs, which we'll look at here in the upper right in a minute. It's passing in the same kind of arguments. So the length n and the pointer to X and Y, but these are the pointers to the data that's been allocated on the GPU and has been initialized on the GPU. So DX and DY have been filled in with their values, and they've been allocated they've been allocated on the GPU. And I'm gonna postpone talking about what's inside this triple chevron syntax, except to say that this is only going to give us a single. It's only going to use a single GPU thread. So that 1 inside the triple chevrons is just going to give us one GPU thread. So what does our code inside of the GPU function look like? Well, the main thing that's different about it, because this is serial code and is just going to run on one GPU thread, is we've put the word global in front of it. And so this underscore global underscore says that this is a function that is going to run on the GPU and is callable from the CPU. So that keyword global will allow us to call it from the CPU, but it'll run on the GPU. So now that was a version of the code, but it's not necessarily, it's a terribly inefficient version of the code because it's using our little wimpy single ALUs on that GPU without really using any parallelism at all. So if we want parallelism, we need to go back and think about this programming model. And unlike the SIMD execution model that you used on the CPUs, we're really going to think of this as having a thread associated with each one of these ALUs. Even though there's a single fetch and decode engine, we're going to just think of it of there being a separate thread associated with each element of an array, for example. And that's associated with that piece of hardware, the ALU that's going to do the arithmetic on it. And then we're going to use that model in order to produce code that will be more highly parallel. So one of the things I like about GPU programming, which I actually don't like about OpenMP programming, is this idea that you're sort of forcing people to think about a parallel algorithm as the default behavior. And if you're going to do something that is only running on one thread, you have to sort of specialize that. And so it does encourage you to think more about a parallel execution model. Okay, so that's still a little bit abstract. What does it look like if we actually try to run this on parallel run our vector add operation on parallel? Well, there are two things that we need to do to use multiple ALUs on a GPU. And we're going to be using one of these SMs at this point in this version of the code, one of these streaming multiprocessors. And so we put a number other than 1 in the second of these triple chevron locations. So we're putting 256. So this says that we're going to run one block that has 256 threads in it. And now inside of this code, we have to do something different to basically turn it into what looks like single program multiple data code, or something that says if each thread is now given this add function to run, how do we make sure that each thread is doing something different? And so what we're going to do is to get a thread ID. So this is like in OpenMP, or as you'll see in MPI, there's always a way of asking, what is my thread ID, or what is my processor ID? So if I'm a thread that's executing this add function, I can ask for my thread ID, and that'll be a number between 0 and 255. And I can then use that to index into the array. So I assign that to this variable index, and I use it to index both of the arrays, X and Y, on both the left and right hand sides. So this is a block of, because I've called it this way, 256 threads. There's nothing in the code that says that this is in the body of the add function that makes it 256, but the way you're calling it is giving you 256. This is actually not a very safe way. Well, let me just ask first, are there any questions about what this code is doing? Okay, so it's not a particularly safe way of writing this code because if we don't call it with 256 256 element array, bad things are going to happen because we're assuming that this 256 matches this n right here in the call statement, and that's because we've got 256 threads that are all going to execute something at their index 0 to 255. If there aren't 256 elements in that array, index 0 to 255, then either you're going to get a segmentation fault of some kind because you're going to be accessing an array out of bounds, or you're not going to be doing the entire computation across the whole array. So let's fix this to make it a more general version of the code. And to do that, we have to recognize that we can't make this number 256 arbitrarily large. We can actually make it, it can be up to 1024, but we can't make it 250, we can't make it larger than 1024 on the Volta. And that number, by the way, on some GPUs is only 512. So there's a maximum number of threads that you can run inside of one of these kernels when you launch the kernel. So what we're going to have to do is use multiple blocks in addition to using, excuse me, using multiple threads within the block. And so we'll write this in a way that we're going to ask for not just what is my thread ID, as we did before to get the index, but also to ask how many, what is the size of the thread block that is, and which is called the block dimension. And so that's written as blockdim.x. And so we've got thread ID .x and blockdim.x that give us the thread ID of this executing thread, and then the total number of threads, if you will, that are in the block. And so we can now make sure that this code runs both on something that's smaller than 256 and something that's larger than 256 element arrays. So it doesn't have to match the number of threads you're calling it on, by making sure the loop bound only goes up to, actually, I'm not sure I put a proper guard in here, but I can certainly handle now arrays that are larger than the thread, than the total number of threads, because I'm going to loop through this. So every thread is going to execute this loop, and it'll do the first element from the first block of 256, and then it'll do another element from the second block of 256, and so on. And we also need to make sure that we don't index off the end of the array by making sure, I guess we've got an I less than n in here. So I think that actually will guard from the overrunning the right end. So this should work even if I call this with a different number of threads than 256, and if n is something other than than matching the thread counts. And as I've written it now, so this will still just run with a single thread block, but I'm going to it's going to allow it to work for these different sizes. And so the 256 threads here, as I said, it has to be less than 10 or equal to 1024 on a Volta, and previously you could have had only 512. And so there's a question about whether this will be running on 256 cores of the GPU shown on the right. The word core here is a little bit confusing. It's not being run on 256 of the streaming multiprocessors, which are often what we refer to as cores in a GPU. It's running on 256 of those ALUs. And this thing is actually going to run on one of those streaming multiprocessors, which has these wider number of ALUs, and it'll iterate through that in the hardware until it's done all 256 of those threads. So
block them related to like within the one single core?
Yeah, within the one single core, it's going to pick up a chunk of the threads and execute those threads, and then remember, because of the idea that we wanted to have a larger number of threads than we had ALUs, because one of the threads might get stalled waiting for something like a memory operation to complete. And so this 256 elements, these 256 threads that we're executing here may be executing on less hardware. This is part of what the GPU is trying to virtualize for you, so you don't have to worry about exactly how many hardware threads there are. And we can get into something called warps, which is the hardware mechanism, which would be something smaller than I think it's 32 on the Volta. So it would be executing a chunk of 32 at a time and cycle through them. Okay, so let's see. We can now also generalize this to run on with multiple blocks, which allows us to get past the 1024 limit. And we do that by, for example, there's some arithmetic up here to say, how many blocks do I need versus my block size? In this case, I picked a block size of 256. Maybe the optimal one would actually be 1024, but 256 is also something possible to use. And so you pick that block size. So that's the number of threads that are going to be within a block. And if you have n that's larger than 256, then this next assignment statement, the num blocks, is going to say how many blocks do you need in order of size 256 to make sure all n things are covered. And so that's what this n plus block size minus 1 divided by block size is doing, is just dividing, basically it's dividing block size by n divided by block size. And the extra stuff here is to make the round off work correctly, to make sure you have sufficient number of blocks, even though the last one won't be full. And then when we call the add function, we call it on the number of blocks and the block size. And so this code here will still perform correctly, and it's still looking at the thread index and the block dimension is the size that they're jumping between. And I need to make sure that I've actually got my global index correct here. So I might check that later. But anyway, so this code is running through, it will run on multiple blocks here. And I believe this index, I do need to make it add on the block dimension. We'll see what that looks like in a minute as well. So this shows the max thread block size about 2/3 of the way down here as 1024 on a number of these different machines, these different GPUs, all NVIDIA GPUs. I should say that this is a very NVIDIA specific lecture because we're using CUDA in this class, and but there are GPUs from AMD and Intel. And in fact, some of the big DOE machines will have some of those kinds of GPUs in them in the future, but the ones you'll be using in this class are NVIDIA machines, and they are running CUDA. And so just makes it a little bit more concrete to refer to these NVIDIA processors. Okay, and so you can see a bunch of other things. This is a teraflop number and stuff like that. I'm not going to read through this. It's mostly for your reference. Okay, so a little bit more about these indices. So just to kind of get your head wrapped around what we're doing here is we've got a big array of some arbitrary size, and we want to figure out which element of that array each one of the threads should be executing. And so what we're going to do is to use the thread ID, which is threadid.x, and that's a CUDA built-in function or built-in pseudo constant that I can get out. So it's a different value for each thread, 0 to say 255. And that gives you the index within your block. And then if you want to access some arbitrary element in here, you say, well, what is my block ID? And so if I'm in block ID 2, then I multiply that times the block dimension, so the total number of threads in each one of the block, which is equal in this case to the number of elements that are in the array in each block. And so I use the block dim.x to get that size. And then I add onto that my thread ID, which says my relative offset within the group of thread, within the thread ID.x is where I am sort of, inside of this thread block. And so this index expression here will give you this element of the array, the index 515. And it's important to realize that CUDA is providing you with these indices, your thread ID, it's telling you how many threads are in a block, It's telling you what your block ID is. So you know which block you're in, which thread you are within the block, and then how big each block is. What you do with that is entirely up to you. And so you decide that, for example, I have one big vector on which I'm doing an add, and I want each thread to be mapped cyclically around, that is, thread, 0 gets the first element, 1 gets the second element, and so on. And so I'll just map it around that, wrap it around that way. And then you decide, for example, if you've got an array that's larger than the total number of threads, how to make sure that each one of the elements gets a value executed for it, so that it gets filled in. Okay. And so I will go back and check that code on the previous slide. There's a question about whether I had a sufficient guard to make sure that I was stopping at the right place. And then the question is, can the number of blocks and block size be adaptable to the array size? That is the problem size. Yes, they absolutely can. In fact, the code that we wrote, what we had back here, actually is adapting the number of blocks to the block size, but you could make this block size be some expression that depends on the n, on the input size. But typically, this is a very common pattern. What you should see here, which is to have a fixed block size of whatever you want it to be, and that may be based on how well you think the hardware is going to execute a certain number of threads. Remember, you want lots of threads to mask the latency of operations, although if you've got a bunch of things that are going to be coming out of registers, because let's say you're doing dense matrix multiply, you may actually want smaller number of threads because that may make it more efficient. You're not cycling through all these different threads. So that tends to be a number that you pick based on hardware and sort of the efficiency, maybe the computational intensity of what you're doing, and not so much specific to the size of the problem. And then the number of blocks gets calculated based on how big your block size is. And let's see, the question in here is, do I need to have the stopping loop condition be n minus stride? I think you still want to, you still want to stop at n, because if you've got a block size that, a number n that is not divisible by the block size, you need to make sure that you execute those last set of elements in there. And so hopefully this I minus n is going to cause just the threads that are sort of before, that have an element left in that last block, should be executing it, and not the ones after that. Okay. All right. So, you might wonder why I had a .x inside of each one of these things for asking what my block ID is, that is, which block is this thread in, and which, how big is the block, how many threads are in the block, that is, and what is the ID within that thread block. So all of these have a .x. And that's what happens if you're dealing with a one-dimensional grid of one-dimensional blocks. And that's a very common case. But the designers of CUDA were worried that a lot of people wanted to write code that has multi-dimensional arrays. Let's say you're doing matrix multiply and you want to deal with 2D arrays, or you're doing a 3D structured grid code of the kind that Jim talked about last week, and therefore you've got a 3-dimensional mesh. And so rather than making the programmer kind of keep all of that mapping in their head, they actually allow you to have higher dimensional sort of virtual mapping, if you will, of the threads and the blocks within what's called the grid. So the grid is the kernel that you launch, is also called the grid of threads, and within the grid of threads are blocks of threads, and within the blocks of threads are threads. So you can also have a 2-dimensional grid of 1-dimensional blocks, and in this case I would be using .y in addition to .x to get the y dimension and the x dimension out of the two-dimensional grid of blocks. And so I'm using that on the block ID, .x and .y, as opposed to using just the .x as I would in a one-dimensional case. And this is just the kind of mapping in your mind that, as I said, this is just to help you make it easier for you to do the mapping onto the hardware. If you want to think about your processor grid, your set of processors as being laid out in a 2D or 3D grid. And you can have a 2D grid of 2D blocks, then you're using Ys in both the grid dimension and the block dimension. And then you've got, you can also have, you can actually go up to 3 dimensions. In fact, the type of these things is called a 3dim, I think 3dim or dim 3, the 3dim, and that is giving you the up to 3 dimensions that you can use in laying out, thinking about how your threads are laid out in the physical hardware, but it's really just a logical representation of where those threads are living in that space. So you can just think of all these little tiny cores, which are really ALUs, as being as just being in some kind of a shape that makes it easier for you to think about your algorithm. Okay, so I chose vector addition very intentionally because it is a problem that doesn't require any sharing. Each one of the elements of the array can be computed without accessing any other elements of an array. And then you can, but of course, in a lot of computations, if you want to do anything interesting with these threads, you're going to have some sharing. And if you're going to have some shared variables of some kind, some way of sharing information between them, you're going to also probably need some synchronization. So the memory system on these GPUs is quite complicated, and complicated in a different way than in a multi-level caching system. In a multi-level caching system on a CPU, it is it's the hardware's responsibility to figure out what goes into the L1, what goes into the L2. If something is being shared by another processor, another core on that same chip, it has to make sure that you get a consistent copy of it. We talked about that and talking a little bit about how the hardware works, but in a GPU, it's going to be much more under your control as a programmer. And so most of these are not caches. They're what we'll also often call scratchpad memory, which is similar in that it's a little bit of fast memory that sits, say, on the chip or nearby the chip if it's HBM, but that is high-speed memory. But it's going to be your job to move things in and out of it, rather than having it be the job of the hardware to do that. And so it's quite different in that regard. So this is a cartoon again of what a typical GPU will look like. And it has both, so in this case, we've got 4 threads. We've got 2 blocks. So we've just got 2 threads in each block. Each one of those threads has a register associated with it. Now, physically, these might be kind of one wide register. If you're thinking more like a SIMD unit, right, that would be a really wide register. But logically, there's really a register associated with each one of these threads. And there's also some local memory associated with each thread, where if things don't fit in memory in the registers, they may be sitting in local memory. And the compiler is going to be generating the code once again, as it does on a CPU, that takes things from local memory into the registers. But for the most part, you're going to want to keep things in registers, because it turns out this local memory is actually quite slow. So you want to try to keep things in registers as much as possible, which means that one of the things that you worry about a lot more in a GPU than you do in a CPU is, yeah, you worry on a CPU about whether or not your data structure is going to fit in registers, but here you really have to manage it much more carefully. And you can easily run out of the physical memory, the local memory, or what we'll talk about in a minute, the shared memory on one of these GPUs. So you really have to be much more conscious of how much memory is available in the GPU. There's no virtual memory system moving things back and forth for you. So in addition to the registers and local memory associated with each thread, and that's their own those local values, per thread values, there's also some shared memory. And I have to say, I always get very confused by the terminology shared memory, because it's sort of like, it's kind of like glasses half full version of shared memory, which is, I'm going to call it shared because I'm sharing it with all the other threads in my thread block, but I'm not really sharing it with anyone else outside of that thread block. So it's a very limited sort of shared memory, but it's shared within a block, as you can see from this cartoon. Now, there's other kinds of memory. We won't talk much about texture memory and constant memory, although they are pieces of the GPU that for some computations you might want to optimize for, certainly for graphics sort of computations. But global memory, or what's also called device memory, is also very important, because that's the way you get back and forth between the CPU, and also a way that you can share things across the blocks. So the blocks can't see each other's shared memory, but they can see things that are in global memory, and the CPU can also see things that are in global memory. And so this is when you do those CUDA mem copies, that data is going from, say, the CPU's memory, which I haven't shown here in its detail, into the global memory on the GPU. And so those are the different types of memory that come up. And these costs, once again, can be quite a bit, like even a factor of 100 slower to access global memory than to access, say, the shared memory. The shared memory is very fast, almost as fast as the registers, whereas the local memory is actually quite a bit slower, and the global memory is even slower. Okay, so so what are we going to do here is have a hierarchical parallelism strategy. We already saw this a little bit, that we're going to use both blocks and threads, but when we talked about it in the context of vector add, we didn't need to worry about what was shared and what was not, because every thread was just accessing one set of elements from the input arrays and the same set of elements from the Y output array. And so we didn't need to worry about, you know, what other values could it see. And so when we now have these two levels of parallelism, which we have to have, because unless you want to restrict your applications to things that only have arrays of size 1024 or smaller, you're going to be stuck with this and that level of parallelism, which will also not run very efficiently, because you really need more parallelism to make these GPUs run efficiently. So because we have a limit on the maximum number of threads per block. And by the way, this is all related to the fact that you've got some very expensive memory that they're sharing. You can't make that too big, or you can't make it very fast. All those kinds of things are driving some of these kind of what seem like kind of arbitrary limits. And so you're going to have two levels of parallelism, and hopefully share things more frequently with the processors within the thread block, and less frequently with the things between different thread blocks. Okay, so here's what our picture looks like now. I've gotten rid of all the details of all the different kinds of memory. Let's just look at shared memory and local thread memory here, which would include, kind of implicitly including this, the registers in this per thread local memory. And so here's our thread block that has some block of shared memory. And that's just shareable by all these threads up to 1024 that are in the block. And in order to get that shared memory, we need to declare a variable with the underscore shared as part of the annotation in front of the declaration. So variables that are underscore shared, and that can be a scalar variable as well as an array, is going to be allocated per block. So there'll just be one of them per block. Other variables in your code are going to be allocated in the per thread local memory. And so, and you have to be sort of careful to keep in mind exactly where arrays and things like that are laid out. Okay, so in order to look at this issue of sharing, I'm going to look at a stencil example. This is also a bit of a contrived example in that all I'm doing, Jim talked about some of the real applications that use stencils last week, these structured grid computations. This is just a one-dimensional stencil, which he talked about. But in this case, all we're going to do is sort of a silly computation, which is to just add up 5 elements of the input array and put the result in the output array in the middle location. And I'm not going to show this code, but we're also filling in the ends of it with you know, assuming there's sort of zeros hanging off the ends here that I haven't seen. So we get ones in the I guess we're just filling in the one is being carried down. But these middle elements, like the 5 is the sum of all 5 of the ones on the left, and so on. And the 14 comes from the things that are outlined in yellow there. So this is what's called a 5-point stencil. It's accessing 5 elements of the X vector and writing the result in one element of the Y vector. And so you can also think of this as a one-dimensional stencil with a radius of 2, because it's going 2 to the left and 2 to the right. So in this 1D stencil example, we can have a radius 2, we can have a radius 3. We're going to write this code in such a way that we're actually referring to the radius as a variable, so we can have it execute with variable widths. And each thread is going to process one output element. It's going to be responsible for writing that one output value and then reading the 5 or 7 or whatever it is input values in order to add them together. And so what this means is that the input values elements are read multiple times. Each thread, for example, is going to be over all the threads. Each one of the input values will be read 5 times if it's a 5-point stencil, 7 times if it's a 7-point stencil, and so on. So you're reusing those inputs, and you would like to take advantage of that in your code. You don't want these values to be sitting, these input arrays to be sitting in the device or global memory, which is very slow, as I said, and accessing that slow memory 5 or 7 times. You want to put it into something faster. And so what you're going to do is you're going to put it into shared memory, where it'll be faster to access and can be shared by all of the values that are all of the threads that need those 5 elements, or that element 5 times. Okay, so if our threading strategy here for our for the stencil computation is going to be to divide the output array into blocks. Although it's shown here with only like 8 elements per block, in general, this is going to be, of course, a larger block, let's say maybe 1024 threads, and therefore 1024 elements, because we're going to have 1 thread per element of the output array. And each of this idea of having each element computed by a single thread is often called an owner computes rule. We're going to see that come up in a lot of other paradigms. It's often a way of avoiding certain kinds of race conditions, because if only one thread is ever responsible for writing into the output, then you don't have to worry about 2 different threads colliding when they're trying to write that output. So each one of this block of threads then is going to be computing a block of output elements, and it's going to write that block of output elements back into the global memory. So the idea is we're going to be that we'll not only have this temporary copy, but we're going to actually be overwriting it and updating it with these values, and so we're going to write the output element directly, I think, into the global memory. Okay, so what does this code look like? Well, if there's this block, thread block here in the middle that has 8 threads in it, and therefore 8 elements of the array that it's responsible for updating, that thread block is going to make a temporary array that is big enough to hold those 8 elements plus the size of the stencil, the radius to the left and to the right. And these are often called halo regions, sometimes called ghost regions, and it comes up, you'll see this again next week when we talk about message passing. It's a fairly common way. And even sometimes in OpenMP and shared memory code, we'll do something like this, partly to avoid having multiple threads updating the same value. So, we'll make this temporary array that's going to be declared in GPU memory, and it'll be in the shared memory, so it'll be fast to access. And then we have to copy the input values into it, and also then once we've computed the outputs, we'll copy the outputs into the global memory output array. Okay, so I need to have 2 indices so that I can keep track of my local index within this local temporary copy, which is something that has size, 2 times the radius plus the block size, and then my global index, which was the pointer or the index into the global array of whatever size n is the input. And so we're going to compute the global index G index with this thread ID X plus the block ID X times the dimension of the block. So this is a very typical sort of idiom for computing a global index within any array, because I want to think of that array as being spread out where each element is on 1 thread. And so that gives me the global index within the input and output arrays. And then for the temporary array, which is just allocated within a thread block, the local index we're going to use is for kind of my threads index is going to be my thread ID plus the radius. That's to deal with the fact that I've got 2 elements, the radius of elements hanging off to the left. So my local index, in order to get the local index and global index to line up, that's the expression I need for L index. So the stencil, here's the stencil kernel code now. It's taking in these 2 arrays, the input and the output array, or pointers to them, and it's allocating a temporary buffer. And by the way, these are assumed to already be in the GPU memory in this global function called this stencil 1D function that we've allocated the input output in global memory so the GPU can access them. And then we're calling we're making up a shared array of size, block size plus 2 times the radius to get the halo regions on both ends of it, and then compute the global index and local index as I showed in the previous screen, which kind of, you can see in the picture up here how the temporary array has gotten allocated. And for the input array, at least, what I need to do is take the values that are in the input array and copy them into the temporary array. And the whole point of all of this, right, of using this temporary is I'm going to do that copy operation once and then reuse it radius number of, or radius times 2 plus 1 numbers of times, right? So that's why I'm going to go to the trouble of making this temporary copy, so I don't directly access the input over and over again as we're running through the stencil operation. So here's the assignment that in parallel with each thread using its own index is going to copy the temporary, copy the input value at the global index into the location of the local index. That'll fill in all of the middle values that are non-halo values inside the temporary array. So at this point, the temporary array has been initialized with those input values. And notice that if there's other SMs in my GPU that are running other thread blocks, which is what will happen, that those thread blocks can be executed on other of these streaming multiprocessor cores. They can all be doing this in parallel and it's all fine, right? These input values are read-only. It's somebody else, some other SM has its own temp that's been allocated, or at least logically within some other thread block, whether it's on the same SM or a different one, it's going to allocate that temp array, and it's been filled in as well. So all of this can be happening in parallel across the entire array. And then the one thing you have to do is to fill in the halo regions. And so to fill in the halo regions, and this is also sort of a common style that you'll see, but maybe it seems a little bit odd, which is I'm going to just say, is my thread ID, let's say that my radius is 2. I'm just going to say, is my thread ID either 0 or 1? And if my thread ID is 0, I'm going to fill in both the first and the very last element. And if my thread ID, at least I think that's the way I've written it, and if my thread ID is 1, I'll fill in the second and the second to the last element. And so that's what these assignment statements are doing, is with just these 2 statements, it's filling in one in the front and one in the back. I don't need a loop here because I have all of these threads executing in parallel. And the only threads that are going to execute this are the ones at the beginning that sort of own these first 2 dark blue things. Logically, those are the ones that are going to be computing, but they're going to go ahead and fill in say the 2 orange ones to the left and the 2 orange ones to the right. And then so we've got this stencil code that is running here, and then we can actually apply the stencil. So this is a continuation of the previous code. So each thread now has its own local variable result, which is shown up here in the picture as a separate variable. It's not an array, and it gets initialized to 0. Then it runs through and computes a loop, which gets all of the from the minus radius to plus the radius, including the element in the middle. We're adding all of those elements together into result. And then at the very end, I'm going to actually write this result out to the output array, which is out in shared memory, out in global/device memory, not in shared memory, because that's not visible by the CPU. So this last assignment statement will put it out in the data structure that's visible, that can be copied back to the CPU with a CUDA-MEM copy. Okay, so there's a problem with this code, which is a race condition. And because I should have asked you what it was, except that I know people can look ahead in the slides anyway. So the race condition comes up from initializing that halo region in that temporary array. And so the problem is that you could have, while threads, say thread 0 and thread 1 are filling in these 2 halo regions, thread 7 or whatever can be going through and accessing the second to the last blue element to fill it in, and it can run into the halo region, go read that value, because there was nothing preventing it from going ahead, and it doesn't have these 2 extra assignment statements to fill in the left and the right halo regions. And so, well, let's see, if it's thread 7, maybe it does. But in any case, it could run a little bit faster, get ahead, and it could access those values when they haven't yet been filled in the halo region. So the problem is that these temp values might not be updated before the temp value is used here in the last line of code on this slide. Okay, so, and we need to, there's a little written out example. What we're going to need to do is add some thread synchronization to this. And the synchronization is like a barrier. It's going to synchronize all of the threads that are in the thread block. And so all the group of them, which is the only group of threads we care about because they're the only ones that can see the shared memory, they're going to all synchronize using this sync threads command or statement that's built into CUDA. And that can avoid all different kinds of races, read and write hazards that where you're either trying to write something simultaneously, or you have something, in this case, you have a read after a write that you're trying to make sure the read really gets the updated value of the write after the halos have been filled in. And so this says that all the threads in the thread block have to reach the barrier before any can pass it. You've seen this barrier idea in OpenMP, and you'll see it again when we get to MPI. So very common pattern of synchronization that comes up. And if it's used inside a conditional, you need to be careful. And this is always true of barriers. If you stick a sync threads inside of a conditional and only some of the threads go down that conditional, remember we said conditionals are can be something slow on a GPU because it can cause the threads to diverge and some of them to get masked out. But nevertheless, sometimes you have to write something with a conditional in it. And if you do that, then you need to make sure if the barrier is nested inside of a conditional, that all of them are going to execute that sync at some point, because otherwise they'll hang. The threads that do execute it will hang waiting for the ones that don't execute it. So here's the corrected code now. Again, I haven't shown you the code from the first slide, which was filling in the halo region and filling in the allocating the temporary array and filling it in. But after that code runs, we just put in sync threads, and then we can go and do the computation. And this causes all the threads to then wait until temp has been fully initialized. So now we get into the subtleties of synchronization on GPUs, which is that threads within a block can synchronize on using the sync threads barrier, but blocks, so the threads across different blocks, cannot synchronize with a barrier. And the reason has to do with scheduling. And this is, by the way, I spent a bunch of time trying to read about exactly how the scheduling works in these, and it's something that they I think intentionally try not to get you to rely on exactly how the scheduling is working, but essentially within a thread block on whatever hardware you have, as I said, you might not have enough hardware to run 1,024 threads at once. You probably only have 32 in a typical, what's called a hardware warp of threads. So it's going to pick off a chunk of 32, but it's going to make sure that all of those 1024 threads get an equal chance to run, even if some of them get really busy doing something, or some of them, for example, synchronize. It'll make sure it picks up the other threads and executes them so they'll all eventually reach the barrier, assuming you've written code in which they all reach the barrier. On the other hand, with blocks, it doesn't make that guarantee. So across different blocks, if you don't have enough hardware to run all of the blocks simultaneously, it may sit there and only run one of the blocks. So the sort of default is that it runs them to completion. And so what this means is that blocks that coordinate across the different blocks they can do that by having some shared variables and doing things like atomic increments to put things into a work queue that is shared across the different blocks. But you can't synchronize and be guaranteed that you can't sit there and wait. You can't just sit there and spin or call a synchronization primitive and expect the other blocks to wait. Now, in CUDA, they have added something called cooperative thread groups that goes beyond these, but for the most part, you're going to use the synchronization barrier synchronization inside the thread blocks. And one other thing you should know is that across different kernel calls, so back up in my CPU code where I'm calling these global functions, there is an implicit barrier between the separate GPU kernels. So that also is a way of synchronizing, although it's a very expensive way of synchronizing because you're going all the way back to the CPU in order to say, I'm done with this operation, now everything is complete. So you don't generally want to do that if you don't have to. And I will also mention here that although the different GPU kernels are synchronized by default with respect to each other, that is, the vec dot doesn't happen until after the vec minus has completed, that if you put some CPU code in between the two, it can actually be overlapped. So that is a standard trick for trying to get better performance of using the CPU and the GPU simultaneously. Okay, so what this says is that blocks really need to be able to operate independently of the other blocks, that we are going to presume that they're going to run to completion without ever being preempted, without being interrupted. So they're not fairly scheduled, unlike the threads within a block. And so they can coordinate, this is kind of funny terminology, they can use these kind of shared pointers, but they can't spin on them, and they can't lock something that's going to just sit there and wait for another thread that's in a different block. And this independence also kind of encourages you to not write code that has too much synchronization. So it tends to give you better scalability anyway. And it is more expensive kind of to do any kind of communication between the blocks, because they have to communicate through that global device memory, not communicate through the fast shared memory. So I'm not going to read through this slide, but this just kind of summarizes the different ways of saying things. Here's the DIM3, the thread ID stuff here near the bottom. There's the synchronization primitive, the ability to declare a kernel function. You can also have just a device function that is only callable from a device function. And you can declare variables that are either sitting in device memory or sitting in shared memory. And by default, otherwise they're local to a thread. And there's a bunch of arithmetic operations or standard math operations that you can get on a GPU. There's also atomic operations. These are very important for things like doing any kind of coordination between blocks, is atomic, atomic adds and things like that, or compare and swap. And finally, just to summarize, which we've seen, CUDA malloc and CUDA free, the CUDA mem copy, and there's other 2D and 3D versions of it and so on for the different ways of thinking about the organization of your data structures. There is something called CUDA malloc managed, which is a relatively new feature that says I can actually directly allocate memory that's accessible to both the CPU and the GPU. I would recommend probably doing the explicit copies, mallocs and frees, and then the copies back and forth, rather than this CUDA malloc managed, but it is something that is can make programming a little bit easier when you first get started. So let's see, one thing about warps, and then I'll wrap up here, and kind of how things map onto hardware. I've sort of said this partly in answering questions, but although we have, say, 1024 threads, a maximum number of threads in a thread block, they get mapped onto a smaller set of hardware that's called a warp. And a warp is going to have 32 elements, and that's kind of the logical SIMD width. And there are primitives for programming at the warp level if you want to. It's something that probably only comes up if you're really doing sort of advanced performance optimizations on your code. Each thread you should really think of as being mapped onto one of these ALUs. And that's why I hesitated when I said, when somebody asked if it was mapped onto a core, because we think of this whole thing as a streaming multiprocessor core, but you can kind of think of it either way. And then these thread blocks are going to be scheduled onto one of these SMs, which is the picture over here, whereas a kernel, which is also called the grid of threads, the grid of thread blocks, that's the thing you launch with the triple chevron syntax, and that's going to execute on a GPU, and the work within it can be spread out across the different SMs depending on how many blocks you have. So just to summarize, we say GPUs get their efficiency from having these simpler cores and more parallelism. You can think of it in some ways as very wide SIMD, although they'll call it SIMT, and it's a little bit different in terms of relative to what SIMD instructions look like on modern CPUs, because there's more flexible addressing. They don't all have to just have one address plus an offset. You can do sort of an index thing, which is something the SIMD units are also starting to add. But you can also have some more thread divergence that the hardware is going to try to schedule efficiently for you and not leave so many of the hardware threads idle. And so that's what's behind this SIMT thing. But it's still probably the best way to think about it is one big data parallel sort of operation. And that parallelism is both for giving you parallel performance in terms of the arithmetic, but also for latency hiding. And that's why it's wider than the hardware. And this is heterogeneous programming. You have to manually copy the data back and forth. things like opening files, things like running the operating system are going to happen on the CPU, and the compute intensive stuff hopefully all happens on the GPU. This is massive parallelism is required to get good performance out of these. Mostly that's going to be what I'll call data parallelism. That is doing the same thing on lots of elements of an array, for example, or some other data structure. Not quite as strict as in the CPU that SIMD, as I mentioned earlier, but still in that same spirit. And the threads in a block share this fast memory, which is this shared memory. And they also have these fast barrier operations, whereas blocks are going to share things through the device memory and using atomic operations. And that's the hierarchical parallel programming model on GPUs. And with that, I think I'll just see if there are any quick questions. I know we're over time. And if not, we'll wrap up. And on Thursday, I may say a little bit more about GPU programming, but mostly we'll be talking about data parallel algorithms, which is a very elegant way of thinking about parallelism that gets used in a lot of different programming models, but is especially important. A lot of these algorithms have been inspired the fast algorithms that people are running on GPUs. All right, thanks very much.